Hello, guys. This is Physics Lab 5, the world's largest rope swing by Alexander Lavrenyuk. So you see table of contents, and we jump to the introduction. We were using three main laws, which was Newton's second law, that's the acceleration of the object depending on its mass and net force acting on it, and that we also used Hooke's law for sprints to find the tension of the sprint. Then also we used energy principle, which states that the energy cannot be created nor destroyed, and we used a really nice formula for the energy of the sprint, which comes from both of the mentioned laws. Then this is a preview of the graphs of the results, but we'll get to them later. Initial conditions. Assume that the human is an average human because we do not know their mass and they look pretty average. So I would say that they're like 70 kilograms as an average human. The rope is an average climbing rope. So I just found information online, which was 11,000 newtons per meter, and rope length was 47.24 meters. The initial position was obvious, and velocity is zero because we do not account for the jump, as there is no way to calculate with what speed the human was jumping. So this is experiment. If you want, you can just find the video online, and yeah, that's like pretty much just jump all around this boulder. So the computational model, the left part, you can see the visualization and the graph part, and a little bit of the system properties and initial conditions on the right, which we already mentioned before. Then the second part, it calculates the basic information like the starting energy. And we also include the T, which we'll use to find the maximum tension of the rope, which will happen obviously at the bottom because it's a circular motion. So then we just conduct a loop in which we calculate these energies and we plot them to find out what we were doing. And also you can see the velocity and position update formulas because they did not fit on the previous slide, so that you can understand where do we get them. Results, we can see that the energy principle holds, delta energy is zero. We can see a very slight change in the spring energy, which also makes sense because there was nearly no extension of the rope at that point. And we can see that change in gravitational and change in kinetic energy, they're pretty much canceling each other out, which obviously also makes sense as we did not account for drag. So we can see the movement by X position, and we can see the movement by Y position, which coincides with how it was in the video, and we can see the model of how it happened. So was the energy principle satisfied? Pretty much yes, because we can see that the change of energy is nearly zero. Obviously, in real conditions, there would be air drag and general loss of energy. So it would not be zero, but it would still be close to a constant value. And the speed would just slowly be decreasing. So we would see a little bit of not particular circle, but like compressed circular motion here. It would be a little bit shorter. And that's pretty much it. And the tension of the rope at the bottom, as we remember, we used the T variable to find it, and we just calculated that it was 2057 newtons. That's pretty much it. And thank you for all your attention.